So sampling converts an analog signal into a number of discrete pulses, each representing the amplitude of the original signal at a particular point. Okay, there's an example of an analog signal there, right? And you can see the sampling pulses on the bottom. Okay, so you can sample them at those particular points, and then the bottom there you will have the sample version of that representing discrete levels. So if you have discrete levels like that, and so those discrete levels can be then now converted to a digital representation. So that's the sampling process. We talk about digital signal processing applications. Where do we use such sampling processing? So DSP, you can think about your cell phone. The microchip in your cell phone is a digital signal processor doing multiple tasks at the same time. Okay, so the other ones are your laptop computer itself. And if you look at the automotive industry, when you talk about the management system in a car, in terms of the engine, the temperature, the speed, the temperature inside the car, so your area, etc. So the DSP application is quite applicable in the automotive industry, in consumer industry, graphics, imaging, industrial, instruments, medical, military, telecommunications, voice and speech. So like the medical industry, you know that you got your scanning processes to actually look at tissue cells of organs in a human body, etc. Instrumentation requires DSPs to be used in those robots, etc. So military, you know that you can have your navigational system using various types of DSP for various applications. Okay, so what does a DSP incorporate? These are three fundamental things, and you actually ought to know this here. This is a typical test or exam question as well. It incorporates mathematics, software programming, processing hardware to manipulate analog signals. Analog and pure sine waves contain a spectrum of component frequencies. So what we understand about a sine wave is that it has the principal frequency and components or spectrum of component frequencies. And these frequencies appear in multiples called harmonics. So harmonics of an analog signals are sine waves at different frequencies and amplitude. Before a signal is sampled, it must be passed through a low-pass filter, anti-aliasing filter, to eliminate harmonic frequencies above a certain value as determined by the Nyquist criteria. Now, so the signal is then passed through a filter, basically in this case, and it will use to eliminate any noise or harmonics, right? And then, so the sampling theorem that we use is determined by the Nyquist criteria. Okay, so I'm sure you have done this Nyquist criteria in electronics 102. And so the sampling theorem has two inputs. One is a singular signal, and the other is a sampling pulse waveform. And the theorem states that in order to represent an analog signal, the sampling frequency F sample must be at least twice the largest frequency component of FA, or maximum FA, of the analog signal. So in other words, so this formula is a bit wrong here, class. I'll just put a 2 in front of it here. Okay, so that's correct now. So when we actually sampling an analog signal, we have to use a sampling pulse, a signal to sample it, and that sampling frequency must be twice the maximum frequency of the analog signal. Then only be able to produce proper samples. Okay, so filtering is to remove all frequency components or harmonics that is greater than the Nyquist frequency. If there are any signals in the analog signal greater than the Nyquist frequency, an unwanted condition known as aliasing will occur, right? So any unwanted frequency above the Nyquist frequency, and the Nyquist frequency is the sampling frequency, which must be twice the highest frequency of the original signal to be sampled. Aliasing is a signal produced when the sampling frequency is not at least twice the signal frequency. Okay, so an application, we all know that the audio signal range is from 20 hertz to 20 kilohertz. 20 kilohertz. And the sampling rates that can be used for audio sampling is 32 kilohertz, 44.1 kilohertz, and 48 kilohertz. And we say we can use 44.1 kilohertz for audio CDs because twice the highest frequency of the audio signal range. So the audio signal range, the highest frequency is 20 kilohertz in this case, and 2 times 20 is 40, so 44.1 kilohertz. So the sampling rate is applicable for audio. Okay, so this here shows us the okay, so looking at the sampling value, okay, the sampling and holding circuit. So you can see that in the first case, your sampling frequency is above the signal frequency, which is fine. Right, so the sampling frequency is in red or pink, and the unfiltered analog signal is in blue. And so there's a certain amount of overlap. And once that is filtered, right, and so you can see that the analog signal is then separated from the sampling frequency spectrum. Okay, so here's a sample and hold circuit. So what's happening on the left-hand side, you can see that the analog signal is sampled at specific frequencies. That's your sampling frequency. And in the box there on the top, you can see those are the discrete values of your analog signal. And once we convert those discrete values into step signal, which is on the right-hand side, and you can see that those are the values that must be sampled. Okay, so the holding operation is the second part of the sample and hold function. Sample must be held constant until the next sample occurs. Gives the ADC sufficient time to process the sample value. Okay, so here again, you can see that your analog signal is shown there in blue in the sine wave, and each step is being sampled, and that is what is being held in the sample and hold section, right? So each one of those steps that are sampled, they must be converted to binary by an analog to digital converter circuit. And then once the step, or once each step is held in the sample and hold circuit, the next step is to put it through to an analog to digital converter process and produce the binary numbers. Okay, so the analog to digital converter, the process of converting the output of the sample and hold circuit to a series of binary codes. Binary codes represent the amplitude of the analog input at the sample times. So we come across another term called quantization. And what is quantization? Typical type of test or exam question. So quantization is basically converting an analog signal to a binary number, right? So process of converting the analog signal to a code. More bits represent a sample value, you get greater accuracy. So you can imagine that the more samples you take, the more accurate your signal is going to be. For instance, in this process here, this is a 2-bit quantization process. What it means is that you're actually using 2 bits to represent the various levels of the analog signal, right? So you can see that you got 0, 1, 2, 3, and those are representations of the various levels of that analog signal. And by looking at the 2-bit process, you have 2 bits to represent each level, right? And The next one now shows a 4-bit representation, right? So here we have a 4-bit representation of the very same process. And in other words, 4 bits of binary information, you get greater accuracy. Okay, so you can imagine that if you got 4 bits of binary numbers to represent any level at any given time, you're going to end up with a greater accuracy of the process. Okay, and so there's the process itself. The chapter, the entire chapter that we're talking about, is that you have an analog input on the left-hand side. It goes to an anti-aliasing filter. It goes to a sample and hold circuit. Then the samples are taken. You have discrete value stair-step values. It goes into an ADC converter. And you can see after the ADC converter, the analog to digital converter, you got binary numbers. You go into DSP for processing, right? And on the output of that, you also got binary numbers, okay? And then they go to a DAC, digital analog conversion process. And there on the right-hand side, you've got a reconstruction filter. And the enhanced analog signal is produced, the output. So there's some questions here according to the textbook there. Let's just bring this down a bit. All right, so some of the questions that they in the textbook so far involved with this section is, what does sampling mean? Why must you hold a sample value? The highest frequency component is an analog signal, is 20 kilohertz. What is the minimum sampling frequency? What does quantization mean? What determines the accuracy of the quantization process? What does DSP stand for? What does ADC stand for? What does DAC stand for? An analog signal is changed to a binary coded form by what circuit? A binary coded signal is changed to an analog form by what circuit? Okay. Okay, class. So I think we're going to stop there for today because I do not want to get too much going into your head right now, into your knowledge area because of the test that's impending. So I think for the day class now we're done for this week online, and this afternoon I'll be doing an online for the evening class, and the evening class will go back to registers, which I did with you yesterday. That's today, and on Thursday I will be doing the what you may call it, DSP section again in class as well. Okay, so this afternoon I'll have a session with the evening class on the registers, and on Thursday I'll have a session with the evening class on this very section on the DSP. And once we've completed with test 1, we will get back to these sections at a later date. Okay, thank you. Lecture is ended. Any questions?
The scope of the test is now.
Hello?
The scope of the test is now.
Okay, the scope of the test, guys, you know that the counter is coming out, the 6 steps counter design. You must know that thoroughly. And I want you to try and go through your theory on the flip-flops, the D-type flip-flop, the SR flip-flop, and the JK flip-flop. You must know the architecture of all three of them, the block diagram, the logic diagram, and the truth table, okay? Then you need to, that's one part, but I'm going to send all of that to you in more greater detail. Then you must know your, what was the other part? Your counter design. You know the counter circuits that we did, the asynchronous and the synchronous counters, right? We did the 3-bit, 4-bit, and the decade counter. Okay, so you must concentrate on the 2 types of decade counters. One was the asynchronous decade counter, and the other was the synchronous decade counter, right? So you must get to know those thoroughly, and then I haven't set the question on the 555 timer yet. So once I've done that, I'll inform you as to what to concentrate on. But on the 555 timer, there's basically two types: the monostable and the astable 555 timer. And there were calculations in the textbook, I think, right? You need to go through a similar type of calculations and expect the same similar type of calculation to come out in your test. And the last part is that you must know the 6-step design thoroughly of that counter circuit. All right. So I'll talk to you when we actually get more clarity on what's going to come out. Okay. All right. That's all for now. Okay. Cheers. Thank you. Bye. Okay. Bye.